talked about pacemaker cells, and I thought it'd be kind of neat to draw out again exactly what these pacemaker cells do and compare them to one another. So we know we have different types of pacemaker cells, and I'm going to use our millivolt scale just as we usually do to kind of compare them. So the first type is our SA node. So let me put that up here, SA node. And those cells start out negative and then they kind of slowly creep up positive. And try to remember why that happens. You know, the main reason for that is that you have the increasing sodium permeability. So at this point, more sodium is kind of rushing into the cell. Sodium is getting in. And if it's getting in quickly, let's say it's like just gushing in, then that line would be very, very steep, you know, something like this. But if it was kind of getting in very slowly, it would be a little bit more shallow. So I've drawn it kind of the way that it usually is drawn, kind of somewhere in between. And when that sodium permeability hits, or when that cell hits a certain threshold, let's say somewhere in there, then it's going to fire an action potential, right? So this is our thresholds for firing, and that just means that the channels for calcium open up. And so they open up and make the cell go positive, and then eventually the potassium channels take over and it becomes negative again. And this part right here then we think of as the action potential. So this is what it looks like for the SA node. But let me now do it again for the AV node. So if there's an AV node, it's going to kind of get up to that threshold a little bit more slowly. But once it gets there, it's going to look basically the same as the SA node, really no different. And it's going to come down again. So this might be the AV node. And finally, we have, let's say, a cell that takes even longer to get to threshold. This would be like the bundle of His. And again, it looks basically the same once it does get there, though. So these action potentials don't really look that different from one another. But the amount of time it takes to get to threshold changes because the bundle of His cells, for example, they are going to be least permeable to sodium, and an AV node would be somewhere in between, and the SA node are most permeable to sodium. So that's why those lines are slightly less steep as you go along. So this is how it looks, and the key difference here is that you're basically extending this heartbeat out, right? This is one heartbeat, and this would be like the SA node heartbeat. But if your AV node was controlling your heartbeat, it might take a little bit longer, something like that. And if your bundle of His was taking control of your heart, the heartbeat would be really long, something like that. So it would take longer and longer for the heartbeat in terms of time, depending on which part of the electrical conduction system is in charge. So let's actually think about that a little bit more carefully. So let's say we have our SA node, and you're talking about heartbeats. Let's actually write out, let's say heart rate. Heart rate is HR, and this is going to be in beats per minute. And then let's say I flipped it around and wanted to know how long one beat takes. So one beat, and that will probably have to be done in seconds. So how would that be for the SA node? Well, we know that the SA node, and this is just a number out of books, you can find them saying something like 60 to 90 beats per minute. And if we took the upper range, let's say you took 90, and try to figure out how long one beat would take, well, you'd say, okay, you have 1 minute gives you 90 beats. I'll put B for beats. And then you have one, let's say, minute is 60 seconds, right? And so the minutes cancel. And now you're left with zeros cancel. 2/3 of a second, right? So 2/3 of a second per beat. And actually, I might even like to, I'm going to erase 2/3 and just rewrite that as 0.66, okay? Just 0.66, something like that. So that's how long it takes for the SA node to fire off one beat. And in fact, just to really hammer home the point, that's this distance right here, right? That's 0.66 seconds. So now for the AV node, we could do the exact same thing. We could say, well, the AV node we know usually is somewhere between 40 to 60 beats. And I'm going to use that number. And this one's really easy, right? Because if it's 60 beats a minute, that means that one beat is 1 second. So that was actually a really quick one. So that's 1 second. And finally, for the bundle of His, I'm going to write that as BOH again. The bundle of His is going to be somewhere between, let's say, 20 to 30 beats per minute. And if we use the number 30, that means that you get a beat every 2 seconds. So every 2 seconds, this will go off. And I know that my picture now, since you know those numbers, it's not going to look as impressive because I should have drawn the bundle of His even more stretched out than it is. But just assume that that's 2 seconds on that graph. So if that's the case, now let's kind of jump back to how we usually think about our heart and the fact that you've got 4 chambers, right? And the conduction system is actually going to go through all of that and starts here in the SA node, goes down to the AV node, and then you've got the bundle of His somewhere down there. And you've got connections down there. And you might be thinking, well, wait a second, you haven't drawn in all of the rest of the electrical conduction system. And that's true, but for right now, let's just focus on these 3 parts, right? So you've got AV here, and you've got the bundle of His over here, BOH, there. So you've got these 3 parts, and they're kind of spaced out, right? Like this is 2 centimeters apart, let's say. I'm just kind of guesstimating, and this might be, let's say, even closer, let's say 1 centimeter. So these are kind of anatomically how they're laid out in terms of how far apart they are from each other. So the question might come up, how exactly do you explain the fact that it's always the SA node that fires off, right? It's never your AV node or your bundle of His. We always say, well, he's in sinus rhythm, right? And what does that mean? Well, someone says someone is in sinus rhythm. All they're saying is that the SA node is what's controlling their rhythm. So sinus rhythm, you might hear that actually a lot on TV shows. I've noticed they like to throw that term around. And it just means that you're in a rhythm controlled by your SA node. So how does that work exactly? Because if it's firing every 0.66 seconds, that's fine. But how come these 2 other, pacemaker cells aren't ever firing? Well, it gets back to basically trying to beat them out. So if you can get a signal from your SA node, this is your, let's say your SA node, kind of from that drawing above, this is your SA node. If you can get it to your AV node faster, if you can get that signal there faster than it would fire, then you've beat it out. So basically, if you can get there a signal from the SA node over to the AV node, if this happens in less than, 1 second, then the AV node is not going to get a chance to fire before you're already firing for it. So this is the race, right? The SA node is basically trying to get a signal over there quickly. And these distances that it has to cover, we said about 2 centimeters and about 1 centimeter. So what is the math? How does that work out? So you can actually look up these numbers, and it turns out that if you check it out, these conduction velocities are really, really fast, right? So it's about 0.5 meters per second up here, and it gets even faster as you get along further. So it's about 2 meters per second here. So these are the velocities of the signal, how fast the electrical conduction system is actually sending along that signal. And those are the distances. So if you think about it, if you just multiply them, you should be able to get a time, how long it will take a signal to get from the SA to the AV node. So we know that the SA node fires every 0.66 seconds, right? That much we figured out already. So the question is, can it get a signal to the AV node before the AV node fires by itself? Can it get a signal down there in less than 1 second? You're trying to beat out this time. And can it get a signal to the bundle of His in less than 2 seconds? You're trying to beat out that time as well. So let's figure it out. So this math works out to, let's see, you got 0.5 meters, and you're going to want to end with a time. So I'm going to put 1 second up here. And you have, let's say, 1 meter is 100 centimeters. So the meters cancel, and you've got 2 centimeters to cover. So the centimeters cancel. So you've got 2 divided by, 50, right? And that's seconds. So it's 0.66 seconds plus 1/25. That's 1/25. Let me make a little bit more space on here, just so it doesn't feel as crowded. There we go. So 1/25 of a second is the same as 0.04 seconds. And that is 0.7 seconds. So far, the signal has gotten here in 0.7 seconds. I'm just going to write that in yellow because this is the SA node signal. 0.7 seconds. Wow, that's really fast, right? Really fast. Let's see how long it takes to get to the bundle of His. So to get to the bundle of His, I'll do that math over here. You have to now add up 0.7 seconds because that's how long it took to get to the AV node. And then you have to add 0.1 seconds. And what is that for? This, my friends, is the delay. This is the delay of the AV node. Remember, the AV node creates this delay so that the ventricles contract just a little bit after the atriums do. So this delay is actually built into the system. The delay is about 1/10 of a second. And then you have to figure out how long it takes to travel. So how long does it take to travel that last little bit? Well, it's going to be going 1 second. It covers 2 meters. And we know that 1 meter has 100 centimeters. And we know that we're trying to cover 1 centimeter. So centimeters cancel, meters cancel, and you're left with 1/200 seconds. So that's how long it actually takes to travel. Travel time, you can think of it as. So that would be 0.005 seconds. So in total, it's now taking us 0.805 seconds. So this is how long it takes to get to the bundle of His. So now, let me write that up here, 0.805 seconds. Now we're really happy because we were able to beat out both the AV node and, I guess from the perspective of the SA node, if SA node cells got happy, that's what they would look like. So it basically gets there really, really quickly is the point. So 0.7 seconds and 0.805 seconds. So that explains at least why you never really see the AV node or the bundle of His cells firing, right? Now going back up here, imagine for a second that you actually had a problem. Let's say you actually had some sort of disease or some sort of issue with your cells, and let's say these SA node cells gave up, right? Well, if they gave up, then no signal would be coming into the AV node, and the AV node becomes your plan B. This is your plan B. The SA node, of course, that's your plan A, right? That's what you're usually doing. But it's nice because you have this plan B, and if 1 second goes by, then without a signal, then the AV node kicks in, and that'll start firing. And you'll have a new heart rate, something closer to 40 to 60, but at least your heart is beating. Now let's say, catastrophe strikes and your AV node is down too. Well, your bundle of His is your plan C. Your plan C. And so now if 2 seconds go by and your bundle of His have not gotten a signal, then they start firing and your heart rate will be somewhere between 20 and 30. So these are the kind of backup mechanisms your heart has to make sure it always beats. And this is kind of one of the neat things that your heart has figured out to create not just a plan A, but also a plan B and a plan C.